Hello friends, welcome you all to the 26th lecture on function analysis and its applications. In this lecture, we will discuss the dual space of C is L1. Dual space means conjugate space. This is the content of today's lecture. The dual space of C is L1. Theorem. The conjugate space of C is L1, that is C star equal to L1. What is C? C is known as the vector space of all convergent sequences. Proof. Let X equal to infinite dimensional x1, x2 and so on xn and so on belonging to C, so that C equal to sequence xn converges to the point L as n tend to infinity. First, let us find the basis for C and obtain the form of the continuous linear functional on C. Now, xn equal to L plus xn minus L, so that we can write x is equal to Le plus summation n is equal to 1 to infinity xn minus L En. So we can write this one. Why? Because here E is 1, 1, 1 infinite time and En, that is En equal to 0, 0 and so on at nth place 1, 0, 0 and so on. Okay, meaning of this is E1 equal to 1, 0, 0 and so on. E2 is equal to 0, 1, 0 and so on. Okay, so that is En is standard basis. Okay, we expand this, we get x. X is x1, x2 and so on xn. Okay, equation 1. Hence, E1, E2 and so on is the basis for C. So that we can write any x in the above form, equation 1. Next, we obtain the form of continuous linear functional on C using previous theorem. Now, F is linear and xn minus L belonging to C0. Since the dual space of C0 is L1, we have f of x, here x is this one, so f of x equal to L into f of E plus summation n is equal to 1 to infinity xn minus L into f of En. That is this. Summation n is equal to 1 to infinity mod f of En is bounded. So, this one can be written as L into Fe, and this one summation n is equal to 1 to infinity f of En into L, okay, plus n is equal to 1 to infinity xn into f of En. So, this expression can be written as this, L common from this and this term, L into f of E minus summation n is equal to 1 to infinity f of En plus summation n is equal to 1 to infinity f of En into xn, this term, okay, equal to L alpha plus summation n is equal to 1 to infinity alpha and xn, okay, where alpha is this f of E minus summation n is equal to 1 to infinity f of En, and alpha n is f of En, n is equal to 1, 2, 3 and so on. Next, we show that the mapping T such that C star to L1 given by Tf is equal to alpha, alpha 1, alpha 2 and so on. Okay, equation 3 is an isometric isomorphism of C star to L1. We show that the mapping T is well defined with the help of previous theorem. Let us define the sequence X belonging to C, where X equal to beta 1, beta 2 and so on beta n and 0, 0, 0 up to infinity. As follows: fx equal to summation k equal to 1 to n alpha k into beta k. Okay, so x can be written as this one as summation k is equal to 1 to n beta k ek. Okay, so f of x equal to summation k is equal to 1 to n beta k into f of ek, and f of ek is alpha k. So we can write f of x is equal to this, where beta k is equal to signum of f of ek bar. F of ek is alpha k, that is signum alpha k bar for k lies between 1 to n, and beta k is equal to 0 for all k greater than n. Now from the definition of norm, since x belonging to C, I like to bounded sequence. So norm of x equal to supremum of mod beta k. Beta k is signum of alpha k bar, that is supremum of mod signum alpha k bar, and by the property of signum function, mod signum function of alpha k bar is equal to 1, that is this one is equal to 1. So norm of x is equal to 1. Further, mod fx, here fx is this, so taking modulus of both sides. So we have this one. Here alpha k and beta k. Beta k is signum alpha k bar. So this can be written as alpha k signum alpha k bar. Okay. And this can be written as mod of, this is mod of alpha k and signum alpha k bar. Okay, and signum alpha k bar is 1, and we have summation k is equal to 1 to n mod alpha k. Okay, so mod of fx is equal to summation k is equal to 1 to n mod alpha k. So this can be written as summation k is equal to 1 to n mod alpha k equal to mod fx. Okay, this is equal to this. F is linear functional. So this is less or equal to norm f, norm x. We can write. And here norm x is equal to 1. Okay. So we have summation k is equal to 1 to n mod alpha k less or equal to norm f. Since summation k is equal to 1 to n mod alpha k is bounded, monotonic increasing sequence, it is a convergent sequence. Hence the sequence of partial sum of the series summation k is equal to 1 to infinity mod alpha k is bounded above, so that summation k is equal to 1 to infinity mod alpha k is absolutely convergent. Hence, mod alpha plus summation k is equal to 1 to infinity mod alpha k is absolutely convergent. Okay, this is absolutely convergent. We have added mod alpha, this is also convergent. So this mod alpha plus summation k is equal to 1 to infinity mod alpha k is absolutely convergent. Thus, infinite dimensional alpha, alpha 1, alpha 2 and so on, which is the image of f under T belongs to L1, so that T is well defined and linear. Next, we prove that T is such that C star to L1 is onto. Let us take beta, beta 1, beta 2 and so on belonging to L1, and so that there is a function g belonging to C star such that T maps g onto beta, beta 1, beta 2 and so on. If x belonging to C, we have x is equal to L E summation k is equal to 1 to infinity xk minus L into ek as equation 1. Okay. We prove that the required g is given by gx is equal to L beta plus summation k is equal to 1 to infinity xk minus L beta k. Okay. This. So beta is g of E. Since the representation for x is unique, g is well defined and linear on C, since mod L less or equal to norm of x, so we have mod gx less or equal to mod beta plus summation k is equal to 1 to infinity mod beta k into norm x. Okay, this shows that g is bounded. Okay, if we divide this expression both sides by norm x, we get norm g. Okay, supremum of mod gx upon norm x. Okay, and this is less or equal to mod of beta plus summation this, that is constant. So norm of g less or equal to some positive constant, that is g is bounded. Okay. Now ge equal to beta and gek equal to beta k for k is equal to 1 to 3. So here this one, and beta k is g of ek. Hence Tg is equal to beta, beta 1, beta 2 and so on, where beta plus summation k is equal to 1 to infinity beta k is convergent. Okay, it should be because here this one, so that T is onto L1. Finally, we prove that norm Tf is equal to norm F, so that T is an isometry. From equation 2, we have Fx is equal to L alpha summation k is equal to 1 to infinity xk alpha k. Okay, here equation 2, Fx is equal to this one. So from 2, we have this. As in the case of G, we have norm F less or equal to mod alpha plus summation k is equal to 1 to infinity mod alpha k, which is norm of Tf using equation 3. Okay, this is equation 3. So norm of Tf equal to mod alpha plus summation n is equal to 1 to infinity mod alpha n, because Tf is the element of L1. Okay, so this is norm of Tf. We can write equation 4. To complete the proof, we establish the reverse inequality. Let us define the sequence xk as follows. Xk equal to signum alpha k bar for k lies between 1 to n, and for k greater than n, xk is signum alpha bar. Then mod xk equal to 1 because mod of signum alpha k bar 1 and also mod signum alpha bar, that is 1. Okay, so mod of xk equal to 1 for all k. So that norm of x equal to 1. Okay, since x belonging to C and if x belonging to C and norm of x equal to supremum of mod xk. Okay, so supremum value of mod xk, here mod xk is 1, that is 1. Since signum alpha bar gets repeated infinitely many times, we have limit n tend to infinity xn equal to signum alpha bar. Using the above special sequence, mod fx, okay, fx is this. So mod fx equal to mod of this whole L alpha plus summation k is equal to 1 to infinity xk alpha k under the mod. So that can be expanded as mod alpha L plus summation k is equal to 1 to n alpha k xk plus summation k is equal to n plus 1 to infinity alpha k xk divided in two terms. Okay, it was summation k is equal to 1 to infinity. Okay, so we have divided here in two parts. K is equal to 1 to n, another from n plus 1 to infinity. So equal to alpha signum alpha bar plus summation k is equal to 1 to n alpha k signum alpha k bar plus summation k is equal to n plus 1 to infinity alpha k signum alpha bar. So this term also can be written as alpha signum alpha bar, that is mod alpha. Similarly, this one also mod alpha k, summation k is equal to 1 to n mod alpha k. And this one here alpha k and signum alpha bar, so it can be written as same. Summation k is equal to n plus 1 to infinity alpha k signum alpha bar. Since alpha k belonging to L1, summation k is equal to n plus 1 to infinity. Okay, here k is equal to n plus 1 to infinity alpha k tend to 0 because alpha k belonging to L1. So this summation less than infinity, that is tend to 0 as n tend to infinity. Hence, taking the limit in the above step, we have mod fx equal to mod alpha plus summation k is equal to 1 to infinity mod alpha k. So that norm of Tf, that is mod alpha summation k is equal to 1 to infinity mod alpha k. Okay, since Tf equal to alpha, alpha 1, alpha 2 and so on, and Tf is the element of L1. Okay, so this one mod alpha summation k is equal to 1 to infinity mod alpha k is norm of Tf. Okay, here already given in equation 3. Okay, Tf is the element of L1. So mod alpha summation k is equal to 1 to infinity mod alpha k is norm of Tf. Okay, and this is mod of fx. Okay, also we know that f is linear functional, so it can be written as less or equal to norm f norm x. Since norm x is equal to 1 because x belonging to C, so we have norm of Tf less or equal to norm of f, equation 5. From equation 4 and equation 5, we have norm f is equal to norm Tf. Okay. Here equation 4, norm f less or equal to norm of Tf, and in equation 5, norm of Tf less or equal to norm of f. It means norm of f is equal to norm of Tf. From the above definition of T given in equation 3, we see that it is linear. Since it is an isometry, it is one-to-one. We have already proved that T is onto, so that T is an isometric isomorphism of C star onto L1. Hence we have C star is equal to L1. In this lecture, we have discussed the dual space of C is L1. These are the references which have been used in this lecture. Function analysis, Dover publication written by George Beckman and Lawrence Naresy. Next, introductory function analysis with applications, John Whaley and Sons, written by Erwin Krejcik. Third, function analysis, New Age International Publishers, written by V.V. Lemieux. And function analysis, Tata McGraw-Hill, written by Waterrudin. Thank you.